To just review the steps. When you're solving a linear equation, the first thing you want to do is to simplify the expression on either side of the equal sign. We do this by removing grouping symbols. Remember that fractions are grouping symbols. The fraction bar is a grouping symbol. So as much as possible, the first thing you want to do is, if there are fractions, you want to get rid of them. And we'll see that in an example in a little bit. And then combine like terms. Then we want to put all the variable terms on one side and all of the constants or numerical terms on the other side. Traditionally, variables go on the left and constants go on the right, but it doesn't matter. We then isolate the variable and solve. In other words, by isolating the variable, we do solve. By isolating the variable, we say what x equals or what y equals or what a equals. We have the variable all by itself with no coefficient other than 1, the number 1, on the left-hand side or the right-hand side, I suppose. And then we want to make sure to check. And the reason we want to make sure to check is that occasionally you will get a solution that looks right, but it doesn't actually solve the original equation. That does not typically happen with linear equations. It does happen with quadratic equations and other types that we will talk about a little bit later on next week. So here's an example from your textbook. We want to solve and then check this equation. Get my laser pointer going here. So we want to solve and check the equation 2 times the quantity x minus 4 minus 5x equals negative 5. So the first thing we want to do is we want to simplify this. We want to simplify this on each side of the equal sign. So the first part of simplification is getting rid of grouping symbols, which include parentheses. So the first thing we're going to do is we're going to distribute to get rid of those grouping symbols. So we're going to distribute the 2 to x. We get 2 times x, that's 2x, and then 4. 2 times negative 4 is negative 8. And so we now have 2x minus 8 minus 5x equals negative 5. And then we combine like terms. And our only like terms here on the left-hand side are 2x and negative 5x. 2x minus 5x, negative 3x. So we have negative 3x minus 8 equals negative 5. And then we collect the variables on one side and the constants on the other. So we have negative 8 here. We want to get rid of that negative 8. So to do that, we add 8. We add 8 to the left, so the addition property of equality says we also have to add 8 to the right. So we have negative 3x plus 0, or just negative 3x, equals negative 5 plus 8, which is 3. So we see now that negative 3x equals 3. So we're ready now to isolate our variable. Now, your book, for reasons best known to your author, say that we're dividing both sides by 3, and then simplify. And that works, but there's a step here that your author missed. When you divide both sides by 3, you end up with negative x equals 1. And then you have to divide again by negative 1 to get x equals negative 1. I think what the author meant to say is we should divide both sides by negative 3. Because negative 3x divided by negative 3 is positive x. Remember, a negative divided by a negative is a positive. And 3 divided by negative 3 is negative 1. And we always, again, we want to check the proposed solution. I'm not going to make you do that. Like, I'm not going to take points off if you don't show that you've checked your work. You may take your own points off sometimes, because sometimes we will make a mistake and we will think x is negative 1, but it's really something else. We always check by replacing, by substituting whatever we saw x would equal, or y, or whatever the variable is. We always substitute that back into the original equation. So 2 times negative 1 minus 4 minus 5 times negative 1, does that equal negative 5? And so we have 2 times, this is negative 1 minus 4, so that's 2 times negative 5. 2 times negative 5 is negative 10. Negative 10 minus negative 5 is negative 10 plus 5, which is negative 5. And yes, negative 5 equals negative 5. That statement's true. And so we can conclude that our solution is correct. It is x equals negative 1. Or if you want to write it like your author does, you could put it in set notation and write it like that. Either way is fine. Any questions about any of that? Anything so far? All right, let's take a look at an example one. I'm going to move over here to the laptop. Hopefully. Looks good. All right. So let's see. Let's do one involving fractions because those can be a little bit trickier. 3x over 2 plus 3 over 5 equals 2x over 5 plus 7 over 2. So the first thing we want to do is get rid of grouping symbols. To get rid of grouping symbols here means to get rid of the fractions. What we want to do is we want to do this in as few steps as possible, usually, to be most efficient. Now, what we could do is first multiply everything by 2 and then multiply everything by 5. That would work. But what we want to do, what's the best choice, is to multiply everything by the lowest common denominator of 2 and 5, or the least common multiple of 2 and 5. The least common multiple of 2 and 5 is 10. So we're going to multiply both sides by 10, and that's going to get rid of the fractions. Again, I chose 10 because it's the least common multiple of 2 and 5. So next, I have to distribute. So we do 10 times 3x over 2 plus 10 times 3/5 on the left-hand side. On the right-hand side, we'll do 10 times 2x over 5 plus 10 times 7/2. So when we distribute, we get 10 times 3x over 2 is 30x over 2 plus 10 times 3 is 30, 30 over 5 equals 10 times 2x over 5 is 20x over 5 plus 70 over 2. Now you say to yourself, or you say to me, what is wrong with you? You said we were going to get rid of the fractions. There are still fractions there. We've accomplished nothing. No, we've accomplished a lot because all of these are fractions that we can now simplify. 2 goes into 30 15 times and into itself once. 5 goes into 30 6 times and into itself once. 5 goes into 20x 4 times and into itself once. 2 goes into 70 35 times and into itself once. So we end up with 15x plus 6 equals 4x plus 35. We've gotten rid of our fractions. Now, we want to group our constants on one side of the equal sign and our variable terms on the other side of the equal sign. I'm going to start by moving a constant. And so what I'm going to do is I'm going to subtract -6 from both sides. And so I get 15x equals 4x, and then 35 minus 6 is 29. And now I'm going to move the 4x over, so I'm going to subtract 4x from both sides. 15x minus 4x is 11x. I get 11x equals 29. X equals 29 over 11, because then I divided both sides by 11. Or if we want to write it like our author, put it in braces. Notice that what we usually want to do is I call this sort of reverse PEMDAS. We do still start with parentheses and grouping symbols, just like in PEMDAS. But then once we start to solve, we want to do the addition and subtraction first. We want to, usually we'll add and subtract as we're simplifying and moving things around. It's easier to add or subtract terms first. And then when you've done all the addition and subtraction you can, then worry about your division. Because otherwise you keep ending up with fractions basically. And we should check this. Unfortunately, 29/11 is not really fun to check, but we will. 3 times 29/11 over 2 plus 3/5. We're checking to see, does that equal 2 times 29/11 over 5 plus 7/2. This is going to be a more complicated check than you actually are going to have to do for anything that you're working with. I think I'm going to do the same thing here as I check. I'm going to multiply both sides by 10, and I'm going to just write that up here rather than rewrite everything for the sake of time. So I can multiply this side by 10. I'm going to multiply this side by 10. And so I'm going to get 15 times 29/11, because 10 times 3 is 30, and 30 divided by 2 is 15, plus 6. 10 times 3 is 30, 30 divided by 10 is 6, or 30 divided by 5 is 6. And then over here, I should get 4 times 29/11, because 2 times 10 is 20, 20 divided by 5 is 4, plus 70 divided by 2 is 35. So I'm still going to need my calculator. It'll be a little bit better. I won't have to deal with complex fractions, which I really don't want to talk about. And of course, other than college algebra. So 15 times 29 is 435. And I'm going to write my 6 and 11ths too. I'm going to get a common denominator. 6 is the same as 66/11. Over on my right-hand side, I have 4 times 29. That's 116. And then I have 35. Again, we'll write this in 11ths. 35 times 11. That's 385/11. So what I get is, on my left-hand side, 501 over 11. And on my right-hand side, I get 501 over 11. Because these two sides equal each other, we know that, yes, x does equal 29/11. And again, for the problems that you have, you will get fractions occasionally as an answer. But when you check them, it'll be a lot simpler and more straightforward than our check was here, since I just made up this problem off the top of my head. So I didn't make it intentionally to be easier or harder, just sort of random numbers. All right. Any questions so far? All right, let's go back then to the PowerPoint, and we'll take a look at an application problem. And so what we see here is a graph that reflects a relationship between a person's sense of humor and their depression after they've experienced a negative life event. I don't know. So the graphs in your book, they aren't made up. They actually come from studies that have been done, usually, maybe always. And so I'm sure that this one is also based on a study. And the study would give us more information than this PowerPoint gives us. What determines if someone has a high sense of humor or a low sense of humor? Is this self-reported by the people? Did, like, the researchers go out and ask, and they found 100 people who said, oh yeah, I have a great sense of humor, and 100 people said, no, I'm not really a funny person? Or was there something else? We don't know. And similarly for depression, my assumption is going to be here that we're not talking about people who have clinical depression, which is a medical condition, right? It's an illness. This is the typical depression that someone feels after something bad happens. We know that even if a person does not have clinical depression, that after a significant negative life event, they're going to feel depressed, right? If something really seriously happens in your life, 8, 9, or 10. So a high event, and again, this is this is subjective. What one person considers really, really negative, someone else might not. But typically, a high intensity negative life event would be something like the death of a close, very close loved one. Maybe a divorce. Maybe a person who has a significant illness or injury that changes their life. All of those would be a very negative life event. Sort of in the middle, sort of an average negative life event then is maybe it's losing your job, but it's not, like up here might be losing your job and you can't find another job. Down here might be losing your job, but you are confident you're going to find another job. In fact, you do. Maybe it's breaking up with a serious partner, but not actually having to go through the legal issues of divorce. Stuff like that. And again, it varies from person to person. And then a low intensity life event might be something like someone you asked out said, no, I don't think so. It's a bummer, but you probably won't think about it in a month. I mean, you might, but not a lot. So a negative life event, we could think of as something that a year from now, we might look back at and say, oh yeah, that kind of sucked, but we've moved on. An average life event, we might look back on and say, oh my gosh, that was really awful. And maybe we haven't completely moved on even. And then a high life event may be something that is really still affecting us a year after, or at least we have really vivid memories of. Now that's my sort of interpretation of this. I didn't read the study because it's not included. So what we're saying is that a person who says or is in this low humor group, the more intense the negative life event, obviously the higher their reported level of depression is going to be. For a person who says they have a good sense of humor or who has been at any case put into the high humor group, it still increases. Like the more intense the negative life event is, the more depressed they say they feel. But they start at lower levels of depression and it doesn't increase nearly as quickly. So we have quite a few differences between these groups that you could do a whole bunch of things with. We're just going to answer one question about it. But first, we talked about math modeling last time. And so here are the equations based on the graph. For the low humor group, that's this looks like blue on my screen, the top line. For the low humor group, the level of depression, that's what D stands for. D is our y-axis in this graph. That number, whatever it is, will equal 10 over 9 times x plus 53 over 9. And x, the horizontal axis, is our x-axis, as it usually is, represents how intense the negative life event was. Was it a 2? Was it a 4.3? Was it a 7.2? Was it 8.6? Whatever. And then so this model, this formula, represents this graph. And then for the high humor group, that formula represents our lower graph, the one that looks sort of purplish. We have the level of depression, D, equals 1/9 x, where x is, again, how intense the life event is, plus 26 nines. Now, I know I spent a lot of time on this graph right now in class. Sometimes that's how much time you should spend on the graph when you look at it in your textbook or on a test or a quiz. It's really tempting to look at a graph, just glance at it, and then move on. But it's also a little dangerous in terms of your score. So try to interpret the graph as best you can. So I'm going to erase some of my ink here because we're going to come back to this slide. And I want to keep some of my ink. There we go. So our question is, we're interested in the intensity of a negative life event with an average that results in an average level of depression of 7/2 for the high humor group. So in this case, what we're looking at is only the formula for the high humor group. And we know what D is. The problem tells us the average level of depression is 7/2. So 7/2 is 3.5. And whoops, and so 3.5 would be, so this is probably 3. So it's going to be halfway between 3 and 4. So 3.5 is going to be right about at this red line segment on the graph. Now we could just read the graph. We could just like sort of go over and say, well, let's see when this is going to intersect this line. When are we going to get to this being at 3.5? And we see that here, it kind of looks like it's right around 4.5. But that is not always super accurate. So we're going to do it with algebra. So what we're doing here is we are solving for x. We are told what D is. We are told that D is 7/2. D is this point right here. So in our formula that we're given in the problem, 1/9 x plus 26/9 equals 7/2. We replace D with what the problem tells us D is for this case, and then we solve for x. So the first thing we've done is we have multiplied both sides by 18. Why are we choosing 18 to multiply both sides by? Why did I pick that number? Why did the author pick that number randomly? Because I mean, it's not random. Why did they pick that number? Don't all answer at once. It's okay. That's right, Owen. It's the least common denominator. 18 is the least common denominator of 2 and 9. So our first goal is to get rid of fractions. That's what we're doing. So we multiply the left-hand side by 18, and then we also multiply the right-hand side. And remember, we are distributing. I'll distribute up here. 18 times 1/9 x plus 18 times 26/9. Remember, when you multiply, you have to multiply every term on the side of the equation by that number. And so we get this when all the simplification is done. Because 18 times 7 is 126, apparently, because 126 divided by 2 is 63. 18 times 1 is 18, of course. And so 9 goes into 18 2 times, so we get 2x here. And then 18 times 26 is 104. No, it's not 104. 18 times 26 is not 104. 18 times 26 is something, it's 468, which divided by 9 gives us this 52 right here. Then, now that we have the fractions taken care of, it's a much easier problem going forward. So we subtract 52 from each side, and we get 11 equals 2x. We then divide both sides by 2, and we get 11/2 equals x. We could check this if we wanted to. I'm not going to in the interest of time. And then typically, usually we're going to keep an improper fraction improper, but sometimes for a word problem, and this is kind of a word problem, we don't keep it improper. It can be hard to tell what to do. Here, since we started with an improper fraction, that's a sign that it's okay for our answer to stay improper, but we do still want to label it. We would want to say something like 11 halves, I don't know, intensity. You want to put some sort of label at. We do not want a naked number for a word problem. And so 11 halves is 5 1/2, and so that would be this point right here. And so this is actually the point that corresponds to 3 1/2 over here. And again, because this line is so thick, I mean, that's part of the problem here. The line is drawn very thickly. So sometimes the formula, you get a more precise answer than the graph. Sometimes the graph comes from a formula. Sometimes a formula is made from a graph. Any questions? We'll go over a similar example in a little bit when we do some more examples. But first, I want to talk about linear equations that do not have a solution. For linear equations, you'll always get one of three cases. Case number one is the most common. In case number one, there will be exactly one solution. And again, far and away the most common. Case number two is what we're going to talk about here. Case number two means there is no solution. In other words, there is nothing that we could replace x with that will make this statement true. There are no solutions to this particular equation. The third case we'll also talk about today. In the third case, all numbers are solutions. In that case, no matter what number we plug into x, the equation will always be true. And we'll see that as well. You will usually not be told that there's no solution. If you're told there's no solution, there's no need to solve the equation. So instead, you just have to learn what to do when you come across that situation. So let's pretend we don't know that there's no solution to this problem. We want to solve it. So what should our first step be? You want to get rid of grouping symbols. So we're going to distribute. And so what we end up with is 2x plus 6 equals 2x plus 8. Right now, some of you may already be able to look at this and say, oh, there's clearly no solution here. Because you're going to end up with something that equals, you're going to end up with a number that equals another number. And that doesn't work. But let's keep going. Let's say we want to get, I'm going to do one more step than the PowerPoint does. I'm just doing my own thing here. We want to subtract 6 from both sides. So I'm going to get 2x equals 2x. Whoops, sorry, it's supposed to be minus 6, not minus 8. Subtract 6 from both sides. 8 minus 6 is positive 2. Okay, now we want to move our variable terms over here. So we're going to subtract 2x from each side. 2x minus 2x is 0. So our answer is 0 equals 2. 0 cannot equal 2. Those are two different numbers. And a number cannot equal a number that's a different value. 7 cannot equal 12. -1 cannot equal 0. 5 cannot equal 13. And here, 0 can equal 2. This means there's no solution. That's what you should write. When you see a case like this, just write the phrase, no solution. Your author uses set theory, uses set notation rather. And so for a multiple choice question on a quiz, instead of no solution, you're going to see the symbol for an empty set. That means the same thing. This is not the number 0, remember. This is the symbol for an empty set. It's an empty set because there's nothing in it. There's no solution. You can write this also if you want. Do not ever say the solution is 0, because 0 isn't. If I plugged 0 in for x, I would end up with 6 equals 8. So 0 is clearly not a solution. So don't tell me the solution is 0. 0 can be a solution to an equation, but this equation has no solution. If for your answer you have a number equals another number, that is your clue. And you can tell that as easily as here. If you have a variable plus a number equals the same variable plus another number, and there's nothing else there, right now you can tell there's no solution, because there's no way that 2 times something plus 6 would equal 2 times the same something plus 8. Just won't happen. Now, you could also try to solve it using this other approach that the PowerPoint uses, where first they subtracted, instead of subtracting the constant from each side, they subtracted 2x from each side. And when you start with that, you get the answer 6 equals 8, which again is still false. There's still no solution. It doesn't matter how you do it. You just need to recognize there's no solution. Any questions about that? All right. Then I mentioned the third case is you have an equation where you could plug any value of x in and it would work. X could be 0, x could be -3, x could be pi, x could be a trillion. No matter what x is, the equation will be true. And so here we have a problem that's going to give us that. So let's solve it and see how we would handle this. So our first thing to do, of course, is to distribute. We want to get rid of grouping symbols. And so we have 4x plus 6 equals 6x plus 6 minus 2x. And then we're going to combine like terms. So we get 4x plus 6 equals 4x plus 6. If something equals itself in the problem, not when we go back and check, because we want it to equal itself when we go back and check. During the problem itself, if your solution is something equals itself, that means we could put any number in for x. Because if x were 1, we would get 10 equals 10. If x were 0, we get 6 equals 6. If x is -2, we would get -2 equals -2. No matter what x equals, it will equal itself here. We would end up basically saying that 6 equals 6, or that 1 equals 1, or that 0 equals 0, depending on how you do it. If a number equals itself, that means the solution is all real numbers. And you can put that a few different ways. You could write all real numbers. You could write the symbol for real numbers, which is an R with an extra vertical line segment. Like that. It's fun to write. Or you could do what your author does and put it in set builder notation. X such that x is a real number. I think it's quicker to do one of these ways, but you're free to do it the way your author wants also. Again, in a quiz, multiple choice setting, this might be an answer choice. So that's what you would see. So you have to recognize, even though you don't have to write it this way, please recognize that this is one way to write, to indicate that all real numbers are a solution. So if one number equals another number, no solutions. If a number equals itself as your final answer, that means all real numbers are solutions. And if a variable equals a number, that means there is one unique solution. And every linear equation will fall into one of those three categories. There will either be one value that solves it, there will be 0 values that solve it, or there will be an infinite number of values that solve it. Questions? All right, let's do some more practice. I'm going to switch back over to the laptop, hopefully. That looks good. That looks good. All right, let's do some problems from the similar problems to those in your book for some of what we've just done. One that let's do this one, I guess. So here, the first thing I want to do is get rid of grouping symbols. So I'm going to distribute this negative sign, or in other words, distribute -1 here and here. So 4y plus 1 minus 5y equals 5 minus y minus 4. Now I can simplify. 4y minus 5y is -y. So I have -y plus 1 on the left. 5 minus 4 is 1. I have 1 minus y on the right. And you might notice these are two different ways of writing the same thing. But let's move on. To show that, I'm going to subtract 1 from each side. And so I'm going to get -y equals 0 minus y. That is -y equals -y. If I were to divide both sides by -1, I would get y equals y. If I were to subtract y from each side, I would get 0 equals 0. I have a number equals itself. Because I have a number equals itself, that means all real numbers are solutions. Or you can write the symbol for the set of all real numbers. And again, I can tell that right here because this is really -y plus 1 equals, just use commutative property to reverse this, equals -y plus 1. And as soon as I see something like that, I can stop. I know right there. If something equals itself, if an expression equals itself exactly, that means my solution is going to be all real numbers. So here, the first thing I want to do is to get rid of the fraction. To get rid of the fraction, I need to multiply both sides by, in this case, just by the denominator 4. Remember, I have to do it to both sides. And I have to do it to every term. So it has to be to the fraction itself, but it also has to be to this -9, even though that -9 is not a fraction. And of course, I'm multiplying 4 times -6. So 4 times 3x over 4 is just 3x. 9 times 4 is -36. -6 times 4 is -24. So now I want to add 36 to each side. So I'm going to get 3x equals 12. And then I divide both sides by 3. I get x equals 4. And I could check this. 3 times 4 divided by 4 minus 9. does that equal -6? That's my original equation. So 12 divided by 4 minus 9, does that equal -6? Does 3 minus 9 equal -6? And yes, it does. -6 equals -6. Then let's do this one. Then we'll do an application problem, then we'll go on to proportions. So here we have the problem 5x minus 3 times the quantity x plus 1 equals 2 times the quantity x plus 3 minus 5. What is the first thing I should do to solve this problem? That's right, I need to distribute. So I need to distribute on this side, and I need to distribute over here as well. So let's do that. 5x, -3 times x is -3x. -3 times 1, that's a 1, is -3. Then on the right, 2 times x is 2x. 2 times 3 is 6, minus 5. So I've distributed. What do I do after distribution? Right, I combine like terms. So on the left-hand side, 5x minus 3x is 2x. 2x minus 3 on the right-hand side, 6 minus 5 is 1. What should I do now? And there's more than one way to approach this. There's more than one right answer or more than one right way to do a step here. So one thing I could do is I could add 1 to both sides. That's right. So I could add 1 here, and I could add 1 here. And so I could get 2x minus 2 equals 2x. So I've just put my constants on this side. So I'm going to put my variables over on the right-hand side. So I'll subtract 2x from each side now. And I get -2 equals 0. What's the solution to my original equation? What's the solution to this equation? There's no solution. That's right. When one number equals another number, there's no solution. Any questions? All right. I want to do an application problem involving formulas. And so I'm going to do number, well, not this number, one similar to 105 and 106 on page 367 in your books. You can follow along at home. And what this gives us is a model for healthy weight. And that model is W divided by 2, where W is weight in pounds, minus 3H equals 53. And here, H is the number of inches a person is above 5 feet. So it does this formula does not work for someone who is not at least 5 feet tall. But if you're 5 feet or over, this will work. And when I say healthy weight, obviously a healthy weight is not one specific value, it's a range. This is a value that would be in the range of healthy weight for somebody who is of a certain height. So let's say we want to find what the healthy weight of someone who is 6 feet 3 inches tall would be. The first thing we need to do is find H. H is the number of inches above 5 feet. So 6 feet 3 inches tall. So 6 feet is 12 inches above 5 feet. And then we have 3 inches more. So someone who is 16 feet 3 inches tall is going to be 15 inches above 5 feet tall. So H here will equal 15. And that is something we often have to do for a formula like this. Sometimes you'll tell you what to do, and sometimes we'll have to do a little arithmetic to get there. So now I can plug H into my formula and I can get ready to solve. I'm solving for W. So W divided by 2 minus 3 times 15 equals 53. I want to solve this for W. Here, before I get rid of my fraction, I'm going to do this multiplication. It's going to make my life easier. So 3 times 15 is 45. How can I get rid of the fraction? I have W over 2. I'm going to get rid of grouping symbols. A fraction bar is a grouping symbol. What do I need to do to get rid of that fraction bar? That's right, Ethan. I need to multiply everything by 2. And so that means I'm going to take my entire left-hand side and multiply it by 2, and my entire right-hand side, which is just one term, and multiply it by 2. So I'm going to get on the left, W minus 90 equals 106. And now, to get W by itself, I just add 90 to both sides. And I get W equals 196. Again, we don't want a naked number. W is in pounds. So minimum 196 pounds. Better still, a healthy weight for someone 6 feet 3 inches tall would be 196 pounds. And again, that doesn't mean that 196 pounds is the only healthy weight for that person. It means that is in the healthy weight range for an average person of that height. Any questions about anything so far? All right. The last thing I want to talk about today is going to be proportion. And first, we need to talk a little bit about ratios. I'm not going to spend a lot of time talking about ratios because that is something that is one of the things that's covered in math strategies, which is the prerequisite for this class. In other words, to get into this class, you either took math strategies or you have a test score that indicates you didn't need math strategies. So you've all worked with ratios dating back probably to middle school, give or take. But I do want to review them just a little bit because they're something that we need to understand for proportion. A ratio compares, should I write this right? Yep, we're good. Okay. A ratio compares quantities by division. And we can express ratios in different ways. We can express ratios using fractions. That is the common way in math, and that's what we will do in this course. We could also express them using a colon, the two dots, one over another, or using words. All of those are used as ways to express ratios. So for example, if there is a group of 60 women and 30 men, we could write the ratio of women to men as a fraction, 60 to 30. We'd still read it 60 to 30 if it's a ratio. We could write it with a colon and we would still read this 60 to 30. Or we could write with the word to, 60 to 30. Any of those ways represent a ratio. It is important to recognize that a ratio could compare anything. So here we have, in this particular group of 90 people, we're comparing, in this ratio, women to men. We could also compare men to women. That would be a ratio of 30 to 60. We could compare the ratio of women to the whole group, 60 to 90. We can compare the ratio of men to the whole group, 30 to 90. So there are multiple ways that we could always write a ratio. It depends on what we're comparing. And when a problem talks about it, you want to read the problem carefully so you understand, is the problem asking you to compare a subgroup, like men or women, to the whole group? Or is it asking you to compare one subgroup, like men, to another subgroup, like women? Or maybe another situation. We have a ratio at Iowa State of freshman students to the overall student body. We could also have a ratio of juniors to the overall student body. Or we could have a ratio of freshmen to juniors, or sophomores to seniors, or sophomores to freshmen. We could have a ratio of really any two things, any two subgroups, or a ratio comparing a subgroup to the entire group. In math, we reduce ratios to fractions to work with them more easily. And when I say reduce, we express them, I should say, as fractions. And we always put them in lowest terms or simplest form. And so in our example, if we had a ratio of 60 women to 30 men, we would simplify that and we would talk about the ratio as being 2 to 1. And again, you could express it with a colon or with words also. With ratios, though, we always keep them as fractions. If we're talking about a ratio, we would never simplify 2 over 1 to be 2. We would keep it as 2 over 1. We would also never change a ratio to a decimal. If we had the ratio of men to women, that was the ratio of 30 to 60, we can simplify that to a ratio of 1 to 2, but we would never write that as 0.5. And so when we talk about ratios in math, we write them as fractions in lowest terms or simplest form. Okay, so that's my quick review of ratios. Now, the point of that is for the next thing in this chapter, which is proportions. A proportion is a statement that says two ratios are equal. If we have a ratio A over B and a ratio C over D, then our proportion is this: A over B equals C over D. And again, for it to be proportional, for it to be a proportion, we're saying that the two ratios equal each other. We solve proportions by cross multiplication. If A over B equals C over D, then it's true that the product A times D equals the product B times C. This is one of the few times when we actually do cross multiply. Sometimes people get cross multiply happy in math because it's kind of fun to cross multiply. It's simple to cross multiply usually. And people try to do it when they probably shouldn't. I've had people try to add fractions by cross multiplying, and that does not work well. Multiplying fractions does also not work well when you cross multiply, but it works well for proportions. If we know 3 values of a proportion, we can cross multiply to find the 4th value. So in this example here, we have the proportion 63 over x equals 7 over 5. And so we see that 63 times 5 equals 7 times x. Again, we go from top left to bottom right, and then we go from bottom left to top right. And it really doesn't matter which one you multiply first. So 63 times 5 is 315. 315 equals 7x. So 315 divided by 7 equals 7x divided by 7. So we divide both sides by 7, we get 45 equals x. Now in this particular case, some of you may have noticed, you may think I don't need to do that here because I could just notice this. I noticed that 7 times 9 is 63. So I know I'm going to multiply this denominator rather, by 9 also. And 9 times 5 is 45. And if you can do it for a problem like this, do it that way. That's fine. You don't have to cross multiply in a case like that. You can just figure out what that proportion is. Often you're going to have more complicated ones where you can't do it just by figuring out, oh, since 7 times 9 is 63, 5 times that number is going to be my answer. Ratios and proportions can be really, really useful in lots of applications, as we're going to see in a little bit. As I mentioned before, we were talking about how did I figure out multiply by 9 here? I asked myself this question: 7 times what number would be 63? And so 7 times 9 is 63. And so since 7 times 9 is 63, then I would have to multiply my denominator by the same number. Really, I'm trying to find an equivalent fraction. Kind of like finding a common denominator when you add or subtract a fraction. When we were talking about recipes a couple lessons back, I mentioned my dad had trained as a baker, and one of the things that he shared with me quite a bit over the years was how, for him in baking school in Minneapolis, ratio and proportion saved his skin. There were problems where you had to do what we kind of did before of, you're making sugar cookies, but you're changing this recipe from 5 dozen to 7.5 dozen. What should you do? And he would always solve problems like that using ratio and proportion, which is more or less what we did ourselves, and we solved them back in the rational numbers chapter. We just didn't call it ratio and proportion. So it can be a really useful to be able to work with. And again, the cross products principle tells us that we don't have to try to figure out, since 7 times 9 is 63, we're going to multiply 5 times 9 to get to 45. That can be a shortcut way if we can do that. But what will always help us out, what will always solve it for us, is cross multiplying. What will always work out for us is to first go from the top left to the bottom right, and then go from the bottom right to the top left. So let's do some examples with proportions. So I'll start with an easier one, and we'll do some harder ones. That's good. So here we have a proportion, x over 32 equals 3 over 24. So to solve this, we cross multiply. We take x times 24, that gives us 24x. And again, we usually write the number first before the variable. And then we multiply the other direction, 32 times 3. 32 times 3 is 96. Now we divide both sides by 24. And 96 divided by 24 is 4. Our answer here is x equals 4. We could check our work. You don't have to. You're not being asked to do that. I don't think here. I guess you are being asked to do it. We can check our work by seeing, are these fractions equivalent fractions? They're equivalent fractions if they would simplify to be the same fraction. And both of these fractions simplify to be 1 over 8. So yes, x equals 4 is the right answer here. Now, a little bit trickier is proportions involving fractions. And I'm going to do one here where our answer is probably going to have a fraction in it too, because I'm changing this a little bit from what your book has. Let me change it a little bit more. We'll see how that works. Not sure how it's going to work. So in a case like this, again, you could treat this as an equation and think about this like, okay, I'm going to multiply, I'm going to find a least common denominator and multiply through, I'm going to multiply both sides by y minus 5 and then y plus 6. And that will work. That will get you the right answer eventually. But cross multiplying is a lot quicker. It makes your life a lot easier. So we're going to have 6 times y plus 6 equals y minus 5 times 5. Okay, so I've cross multiplied. This is supposed to be a y here. No, it doesn't look like one. And now we're going to distribute. So we have 6y plus 36 equals 5y minus 25. We subtract 5y from each side. So we're going to have y plus 36 equals negative 25. And then we subtract 36 from each side. And we have y equals, I'm going to do this on the calculator, negative 25 minus 36 is negative 61. And again, we can check this. 6 over negative 61 minus 5. We want to know, does this equal 5 over negative 61 plus 6? So 6 over negative 61 minus 5 is negative 66. And negative 61 plus 6 is negative 55. And yeah, these are the fractions negative 1/11. The negative 1/11 equals negative 1/11. It checks out. So in a case like this, sometimes people look at this and they think about multiplying through by denominators to get rid of stuff, just like we would typically do, but because it's set up as a proportion, it is much easier to cross multiply. It saves a lot of time. A lot of steps are saved, and in each of those steps, there's that possibility of making an error. And maybe you only have a 1% chance of making an error in each step, but that means if you go through 25 steps, you end up with a 25% chance of making an error. If you only have 5 steps, you only have a 5% chance of making an error. The fewer steps, usually the better. Usually, not always. When we're learning it, it's good to go step by step with things. but cross products are a good thing. Any questions about proportion so far? All right, I want to end with a word problem. This is similar to number 110 in your book, which states that how long we take a shower is proportional to how many gallons we use. In other words, the longer we shower for, the more gallons of water we use. The shorter our shower, the fewer the gallons of water we use. So let's say there's this shower, and in this particular shower, if the shower lasts 5 minutes, it uses 28 gallons of water. I'm changing the figures a little bit from your book. We want to know how many gallons will be used for a 13-minute shower. Now, if it had been a 15-minute shower, my answer would be easy. I just multiply everything by 3. Here it's 13 minutes, not as easy. This is where we set up a proportion. There is more than one right way to set this up. A 5, the problem tells us, I'm going to put the labels in here. You don't have to, but I'm going to. Whoops. A 5-minute shower uses 28 gallons of water. If we take a 13-minute shower, we want to know how many gallons of water are we going to use. This is our proportion. It's important that we have things lined up. If I have minutes on top for one ratio, I should have minutes on top for my other ratio. If I have gallons on the bottom for one, I should have gallons on the bottom for the other. It's important that they line up like that. Otherwise, you will get the wrong answer. There's nothing special about having minutes over gallons. If I had 28 gallons over 5 minutes equaled X gallons over 13 minutes, that's also okay. I would get the same final answer. It doesn't matter how you set it up as long as you are consistent. If I have minutes on top on one side, I should have minutes on top on the other side. If I have gallons on top on one side, I should have gallons on top on the other side. Couldn't you also take 28 divided by 5 and then multiply that answer by 13? You certainly could. In fact, that's what cross multiplication does. All right, so speaking of cross multiplication, let's do that. So we have, and I'm going to ignore the labels except for my final answer. They're just going to confuse us as we cross multiply. I get 5x equals 28 by 13. And so that's going to be 5x equals 364. Divide both sides by 5. And I'm going to get x equals 72.8. And again, for the final answer, I want a label. So, and for a final answer in a word problem, unless we start with an improper fraction, we often are going to want to put it as a decimal like this. It wouldn't make, when we talk about gallons of water, it makes sense to use 0.2 gallons or 0.75 gallons or, 0.289 gallons or whatever. So a 13-minute shower would use 72.8 gallons of water. We could also, from a problem like this, answer other questions. Let's answer another one. So the same setup. This particular shower, 5 minutes, takes 28 gallons. Well, let's say you want to conserve water. You don't want to use more than 20 gallons. If I want to use no more than 20 gallons, of water, how long can I shower for? How long can my shower be for? That's probably not good English, but that's okay. So again, we can still start with our same problem, our same ratio. 5 minutes takes 28 gallons. We want to use 20 gallons of water. We're going to save 8 gallons. We want to know how long should we shower for if we want to use 20 gallons of water. And so again, we cross multiply. 5 times 20 is 100. And of course, x times 28 or 28 times x is 28x. I'm just going to rewrite this in the typical order because that's what I'm used to. We get x is 100 over 28. And again, it doesn't make sense for our number of minutes to be an improper fraction, so we will estimate this to a lovely repeating decimal. We'll say it should be about 3.57 minutes. Actually, we'll say it should be about 3.6 minutes. So if I wanted for this particular shower to use no more than 20 gallons of water, I could shower for 3.6 minutes. And we could figure out if we wanted to how many seconds 6/10 of a minute is, but we're not going to. Questions? All right, I think there weren't any other ones I desperately wanted to do, if I remember right. So let's take a look in Canvas here for a second as we end class today. And let me get your attendance link up here also into the chat. All right, now you don't need my homework, you need your homework. Oh, 2. And I go get to student view to make sure it's actually posted so you can see it. All right. So today we talked about proportions and we finished talking about solving linear equations, including those cases of no solutions or all real numbers or solutions. Previously posted assignments are due still on Friday. There's homework from chapter 5. That's scientific notation and arithmetic and geometric sequences. There's a homework assignment from 6.1, which was linear expressions, simplifying them, evaluating them, stuff like that. And there's a quiz, which covers, I think, 6.1. I can never remember what the quiz covers. I think we've gone through this before. That'll be chapter 5. So the quiz covers mostly the stuff from mostly chapter 5, a little of chapter 5 and a little of chapter 6. 14 questions, some of them are extra credit. Due the end of the day on Monday is homework 6.2. Homework 6.2 it covers what we did in class today. So officially due the end of the day on Monday. Make sure it's done before we go on to 6.3. What we're going to do in class on Tuesday, what we'll do the first part of class is more applications with linear equations. That's what we're going to spend quite a bit of time on. And then we will spend a little bit of time getting started on 6.4, which are linear inequalities. I want to remind you that I think enrollment starts on Monday. We talked about that. We might have talked about, maybe we did talk about that on Tuesday. Today's Thursday. So we did talk about it a little bit because I talked about other math courses and stuff like that, I think. If you have questions about any of that, ask your advisor, or you can, if it's a math course question, ask me, and I will try to help. Again, if you have a question for me, please email me. I've heard that there are issues with instructors not responding to students in a timely manner. I hope that's never me. I hope I always respond to you quickly, or at least relatively quickly. My goal is always within 24 hours, except for the weekends, because weekends are Carl's time. So if you don't get a response from me when you email during the week and it's been a day and you haven't heard back from me, please email me again. I'm not intending to ignore you. Sometimes I just space it out, and sometimes I might not have gotten it, honestly. More likely I just spaced it out. That does happen. Not a lot, but sometimes. So please email me if you have any questions. And when you email a dean to complain that instructors don't respond to your email, feel free to say, but Carl does. That would be great. Have a good rest of your day. Again, if you have any questions, stick around and ask me now or send me an email. Otherwise, have a good day. Have a good weekend. I'll see you on Tuesday. Bye for now.